Okay. Okay. So as usual, I guess the main thing I want to do to start off is to go over any kind of questions you had from last time. I think the last time was a weird kind of mix of something very simple, which is the group U1, and then something kind of arbitrarily complicated and sophisticated, which is the notion of a unitary representation. So some of that, the abstract part of that should have been very confusing, though what I hope got through is more this idea of what is a representation of this group U1, and and what does a general representation look like. So maybe I'll say a little bit more about that, review that when we start, but maybe first, before I get to that, so are there any questions things that people wanted to ask about to start off? Anything from last time?
Yeah, I had a question. So basically, I just have some confusion around sub-representations. And
wait, around what kind of representations?
Sub-representations.
Sorry, I'm not hearing the first part of it. Oh, about representations in general?
Sub-representations.
Sub-representations. Oh, okay, I got it.
And so basically I'm wondering, like, we have, if pi v is some representation of some group on the vector space V,
right,
then a sub-representation for a subspace W of V is pi restricted to W, comma W. So I guess I'm confused about what exactly pi restricted to W means.
Well, so pi is really just a map that for any element of the group gives you a linear transformation on V, right? So if you think of it as if you have a basis, it's just a matrix, for each element of G. But so a sub-representation is basically when you can consistently restrict everything to a subspace. I mean, if you just pick a subspace and then say I want to look at the pi of at these pi of G's, at these linear operators, these matrices acting on vectors that subspace, the danger in general is going to be that the pi of G's, these operators are going to take you out of the subspace. So you have a sub-representation when they don't take you out of the subspace, that if you act with any of these operators on a vector in the subspace, you stay in the subspace.
Okay. So for each G, pi restricted to W of G gives you the same matrix that pi, just normal pi.
It's the same matrix, yeah.
So what matters is just that matrix operating on any vector in the subspace W has to remain in the subspace W.
Exactly, and yeah, that's the condition for it to be a sub-representation. Yeah, right.
Okay, thanks.
Okay, anything else? No.
Yeah, I had a question.
Sure. Okay. Hi. I know.
Hey. So it feels like the only reason I know that charge has a U1 symmetry is because I've been told that charge has a U1 symmetry. And even after looking over the notes and rereading chapter 2 a couple times, I still don't completely understand how we can make the jump. Could you maybe elaborate a little bit further?
Yeah. Well, I haven't really done any physics, and so at this point, charge is really just a word. So I've decided to call actually, maybe let me get started on what I wanted to review last time, and then as part of that, somebody has to mute their microphone. Somebody. There. Okay. Anyway, so let me start a little bit on reviewing what I wanted to say, and then as part of that, explain kind of why I'm calling it charge. But yeah. So let's start with this. So let's see. Okay. So the basics. What you should take away from last time is we're looking at the group G is equal to U1, and that any element of the group U1. So G, you can take group elements, just be, unit length complex numbers, e to the I theta, and then you're just going to under multiplication. Okay, so a representation. Well, what I showed, is that for any any representation of this is of the form. So any rep is can be put in the form that pi of g, or pi of e to the I theta, like is just that it just acts diagonally. You can break up the space on which you're acting into these sub-representations, if you like, in the subspaces of dimension 1, and then on that subspace, it's going to act as e to the I, and then some integer times theta, and then go down to e to the I. And if the representation is n-dimensional, there are going to be n of these integers, and the q j is going to be some integer. Okay. And now so what I wanted to, one thing to notice about this is that you can rewrite this in the form as e to the I times some q, and where this is a matrix. This is a matrix exponential, and then where q is just the q1 down to qn, and everything else is 0. And this is what I called this I called the charge operator.
Professor, sorry, I forget. Is everything else 0 in the other matrix as well?
Yeah. So this is kind of a trivial, maybe because everything is one. All the representations are one-dimensional. You can break it up so that everything is diagonal. Yeah, but yeah, exactly. Okay. Thanks. Okay, so now, so what I want to and I can also note that I can recover. I can, if I just have this and I want to find q, one way to recover it is by looking at the derivative. If you take the derivative with respect to theta of pi e to the I theta, and look at theta is equal to 0, you're going to get, sorry, you're going to get I times q. Right. Okay, so anyway, so this is all just math at some point. This what I'm just doing here is I'm just kind of writing down a general representation of U1, telling you what it looks like. It has this fairly simple thing once you break it up into the one-dimensional spaces. And then the point I wanted to emphasize is that you can actually think of these. You can think of these representation matrices as the exponentials of something fairly simple, and so they're exponentials of IQ times theta, where Q is just this list of integers. Okay. Okay, and I decide, and now this is an example of a, if you want one, this is an example of a self-adjoint linear. This is a self-adjoint linear operator. So it's the kind of thing that you would think of as a quantum observable. Okay. So what I've told you so far in this class is I've told you that in quantum mechanics you've got some your states are just elements of some complex vector space, and your observables are self-adjoint linear operators in the vector space. What I'm doing here is I'm producing an example. So the vector space here is just Cn, and it's a bunch of copies of the complex numbers put together, and the and I've got this general, and in general, it's going to, if there's a group U1 acting on this as a representation, then it's going to be doing this to it. But this is maybe best thought of as the exponential of this, of I times something which is just a bunch of integers. And so this is the thing which we want to kind of assign some physical significance to. We want to call this a kind of quantum version of an observable. And it's just in this U1 case, what I'm saying is that the quantum observables are really just these lists of integers. That if somebody gives you a quantum system and all you ever really know about it is how it behaves under this U1 symmetry, then the only kind of thing quantum mechanics tells you about it is kind of what these integers are, or the only thing representation theory tells you about. But now if you want to kind of assign any meaning to this to charge, so anyway, so this is all just kind of math, and this is just a word at this point. The only connection to physics that I made is by noticing that I've produced a self-adjoint linear operator, and I've told you that those are what the quantum observables. Okay, so maybe maybe better just let me just say this and not do this. So we're going to get to this much later, but it's going to the actual connection to electric charge to charge and to electric charge is going to come about because maybe write that down. So this is now getting ahead of ourselves. So it's called charge because physically, the Q corresponding to U1 action on wave functions so if you've got a wave function psi, well, let me not write it down, but psi goes to e to the I theta times psi, is electric charge. Okay, so one thing about quantum states, the kind of simplest thing about quantum states, because they're complex. It's a complex vector space, is you can just multiply them by e to the I theta. You can multiply them by e to the I theta. And if your theory, and then you can ask, so this is a U1 symmetry of the theory. You're acting on the states by this U1, and it turns out we'll see this a lot later, that when these are the psi's corresponding to to wave functions, the wave functions describing a particle, then the physical significance of this charge operator in this situation is going to be that it tells you what the electric charge of the state is, and that's why it's integer. So I won't. I mean, we won't really. Anyway, if you've seen a lot more about quantum mechanics, maybe this will make sense, but we're not really there yet. I'm just kind of trying to motivate why I'm using this name charge. But does that answer quite the question? That was kind of the review I wanted to do anyway.
Yeah, somewhat. I mean, I guess we're gonna get to it when we get to it.
Yeah. Yeah. So I'm trying to start with very simple, and right now pretty much everything is just simple mathematics. But the name I've given to, so the only physics is that I've given this guy a suggestive name, and I've kind of pointed out that he counts as a quantum observable in my definition of quantum mechanics. That's the only physics we've seen so far. Okay. So anything else about this? So let me actually try this. See if I can do this. So in the book, in the notes, there's a completely mysterious picture. I thought I'd make some comments about it. Let's see if I can do this. Okay. Okay, so you should be looking at this mysterious picture. I wanted to kind of make a few comments about that. That this is, so if you think geometrically about what this mapping is, that's taking you this pi mapping, the one that I unfortunately just erased. Well, here you're group is a circle, and here's the formula I erased. So this is what your representation looks like, is this. And then if you differentiate, and I should have said at beta is equal to 0, you get, well, actually, no, so the mapping takes you from here to here to some point. So this gray blob is supposed to be some version of the space of linear operators, and there are unitary operators acting on the space. So you don't really know what that looks like, but that's the gray blob. So you get taken to a point of the gray blob. If you want to, one thing that mapping does is it takes the identity to the identity, and then now what we're doing though is the whole kind of philosophy here is that instead of trying to study these representation maps in general, because they're very kind of complicated and they're very nonlinear maps, what we want to do is we want to turn the problem into a linear problem. So we want to, in some sense, take the derivative of the map at the identity. So that takes the tangent space to tangent space, and if you know about manifolds, and so in this, so the tangent space, the circle at the identity is just that kind of a copy of the real number line in the imaginary direction, and the tangent space here is going to be some linear space, some more complicated thing, and you're gonna and the derivative of this map takes this guy to this guy, and that's kind of what this is, and that's really what the information that's carried by the by this charge operator. So I'm not sure that this is actually all that useful, but it just kind of thought for some people, if you're trying to understand what this pi actually looks like, this may give you an idea, and it also may explain to you kind of why we don't want to actually compute with it so much. We actually want to do much more simple linear algebra things and talk about just simple linear operators. So I don't know if that helps, but that's at least kind of a motivation for a particular picture. Okay. Okay, so let me so that's the kind of general nonsense about U1. I think maybe there's one other. Okay, there's something which I kind of which is also still in that first chapter, which I kind of skipped last time. Let me kind of quickly say something about that, then we're gonna use that today again. So let me just say this. So recall. So let's go back to. We had at some point I said that there's a basic fact with Schrodinger's equation. Okay, and that Schrodinger's equation was that if you take I times the derivative with respect to time of a state, and so now we want to think about what the state does as a function of time. Let's say that it depends upon time. That's given by some linear operator, some self-adjoint linear operator acting on psi t. Okay, and this is called the Hamiltonian operator, and at this point we don't really know anything about it. But we do know if we're just talking about one of these. We're just talking about one of these finite dimensional state spaces. Then H is just H is a self-adjoint n by n matrix. Okay. So this equation is just an equation for a column vector varying as a function of time, and what we're just saying is that there's the world's simplest first order differential equation telling you how this varies in time, which is given by acting with this linear operator. And so if we, and I'm going to assume that H doesn't, in principle, you can make this more complicated by making H depend on time. But for what I'm doing now, I'll just say H is time independent. And so let's say H time independent. then I mean it's easy to solve this equation. You should be able to solve this equation that psi of t, the state, the vector at a time t is just given. If you put the I over here, it gets a minus sign, and then the derivative of function of time is a constant times the function of time. Is it the answer to that is always the exponential. So this is going to be e to the minus I ht sine of 0. Okay, so these very simple systems that we're going to start talking about, where there's where the state space is finite dimensional and h is just some self-adjoint matrix, then we can immediately solve Schrodinger's equation just by this exponentiation. And so this should look a little bit familiar with what I've been talking about the U1 symmetry. So in the U1 symmetry, I said, if we had a circle acting on states, then the action you would get if you differentiated it, you got this operator Q, the self-adjoint operator Q, times an I. Here, it's really the same thing. So it's much like U1, except no periodicity. So the group is really just the real numbers. Okay, and so I'm going to say a bunch about this later. I'm going to talk in general. Start asking the question. If our group was the real numbers, what are all the possible representations? But you can kind of see that here the group is representation, and here what it's doing is it's acts by time transformations. Okay. So this is very similar to that. Anyway, so this is kind of closer related to what I've been talking about the U1, except that now it's R. But I think what I want you to take from this now is just this, just that that H is just some n by n self-adjoint matrix, and if you exponentiate it, you get the time evolution, you get the dynamics of the system, and we'll see this in a more interesting case later. But you could also do this for these systems with U1 symmetry. And now the thing that I wanted to say that I didn't get to last time is if this is true, so you can, let me just say this here. So the U1 action commutes e to the iq theta commutes with the time translation e to the minus I h p. So if this operator commutes with this operator, that's actually so this is what I won't work out because it's in the notes. But this if for all theta and t these things commute, this is only going to work if the Q and H commute. Okay. So I just wanted to point. So this is a principle that we're going to see time and time again. That that what you really should think of it as a symmetry of the system, as kind of which is going to give you if you want to have a conserved quantity, if you want your values of Q to stay the same as time goes on, then you need this condition. Okay, you have an H operator and a Q operator, and when they commute, that corresponds to the operator that you get by acting by by U1 on it, and that you get by acting by time translation, that these two actions commute. So this is really what I want to say is, this is really when you have a, so this is a, so then the U1 action is a symmetry. Okay, so maybe I wanted to say maybe a few words about this word symmetry, because it's used in a very confusing way, because often people talk about this whole subject that I've told you about, representation theory, as a study of symmetries, but it's really what we're doing often is we're acting on objects, or we're acting on states, not in a way that doesn't leave them alone, so they're not symmetric under the action, but they're moving from they're changing from one thing to another. But physically, what you often mean when you say that a system has a symmetry is you mean that the dynamic, the way you've got some kind of group acting on the system, and it commutes with the dynamics, that the dynamics, the Schrodinger's equation, doesn't change. The action of time translation doesn't change, doesn't interfere at all with the way the group acts. They're two independent things, and that's what I would call as, you really do have a symmetry. That this is a special condition on the Hamiltonian, and it's this condition. So we're going to see this very often, but I wanted to say this. And you know that if you take a standard physics course these days, often when they talk about symmetries, they often start from a very different point of view. They don't start with the Hamiltonian point of view and with the Schrodinger equation point of view. Instead, they start with the Lagrangian point of view, and then what they do is they look at to see how you have a group acting on all your variables, and you see if the Lagrangian is invariant under the symmetry. And if the Lagrangian is invariant under the symmetry, under the group action, then you say you have a symmetry, and you apply Noether's theorem to get a corresponding observable. So this is all kind of coming at it at that problem from a very different angle. That we're not doing Lagrangian mechanics, we're doing Hamiltonian mechanics. And from this point of view, this is kind of where there is no Noether's theorem, and it's really this is the main principle. Okay, so I just wanted to point. So we'll see this again. We'll see this time and time again. Just kind of watch out for this as we, and this is one of the main ways in which we're going to apply group representation theory to physics, is to find cases where this is true, and then we can use representation theory to tell us something about what the states are going to do and what the conserved quantities are. They're going to characterize states as you move along in time. Okay. Any questions about this? This is a bit general, getting ahead of ourselves. But okay, so if no question about this, then let me get on to the next to the material for today, which is more in the chapter 3. Okay, so I think before I say too much about what's in there, before I actually get into the details of what's in there, it's probably a good idea if I give you kind of an overview of what we're doing, because it's a very in this chapter I'm going in the opposite direction of what we're doing with U1. So in the case of the case of U1, what we did is we found the most general representation. Okay, and so what we're going to do today, we're going to do something. It turns out that if you go to you go to the next, instead of dealing with kind of one-dimensional vector spaces, you go to two complex dimensional vector spaces, and then look at a at a bigger group, this group SU2, which we'll talk a lot about. So here we're gonna today. This is the only we'll only consider the simplest non-trivial representation. One thing to say about representation theory is that there's always something called the trivial representation. If you just take all your pi to always be the identity, that's a representation that satisfies all the rules for representation, but it's kind of a trivial one. So the question is, what's the simplest non-trivial representation? Well, in the case in here the simplest one was pi of e to the I theta is equal to e to the I theta. So this was just the q is equal to 1 representation. That's kind of the simplest one. And so sometimes and this kind of representation where you're just taking a if you like, you're taking a matrix and then pi just gives you back the same matrix. That's often called the define. So this is sometimes called the defining representation. And so we're going to do the same thing here, the defining representation. And so pi of G is just going to be G, where G is a 2 by 2 complex matrix. And this acts on our state space is going to just be C2.
Professor?
Yeah.
Just to clarify, the most general representation for U1 is pi of e to the I k theta goes to e to the I k theta, where k is some integer, or what? I just want to make sure.
Okay, so the most general representation. Okay, so the general irreducible. Okay, so the irreducible representations are the So the irreducible representations are the ones pi of e to the I theta is e to the I q theta for some integer, right? So those are one-dimensional, and they're one-dimensional, and they're irreducible. There's nothing smaller. The most general representation is a direct sum of a lot of those. Okay, so what we're going to do here, so this is also anyway, so they're kind of two steps. If you're trying to analyze the representations of a group, the general representation is a sum of irreducibles, and you have to find the irreducibles and make a list of them. And then a general representation is you just have to say which ones you're putting together. Okay. But so here we're gonna the same general thing is true about SU2. That if you want to know what the most general representation of SU2 is, what you have to find the irreducible ones, and then a general one is just going to be a direct sum of some list of irreducibles. So I don't want to, but what I'm not doing today. So here what I'm doing is the problem. So finding all irreducible representations of SU2 is a bit complicated, but it's not that bad. But and we will. I forget the chapter. It may be chapter 9. So we will do this. So what I did last time, which was finding the irreducible representations of U1, it's kind of a trivial or very simple argument, and they're very easy to understand. The problem is that the irreducible representations of SU2 are again, it turns out that the list, you can label them in a fairly simple way, but as they're labeled by positive. So actually, for those of you who already seen this, I don't want to get too much ahead of myself. There will be later on we'll actually answer this question and show why this is true. But they have the answer, which you may have seen, is, and these are often called the spin n over 2 representations. They're given by so v, well, let me call it this way, pi j vj, or vj is equal to c to the n plus 1. Let's call it n plus 1. And then n is equal to 0, 1, 2, etc. And this is called the spin n over 2 representation. Okay, so this will make no sense to you if you haven't seen this before. But if you have seen this kind of subject before, at some point you may have heard about that representations of the rotational group or of this SU2 come in these ones labeled by the non-negative integers, and they're called the spin n over 2 representations, and they're on the complex numbers of dimension n plus 1. So here today we're looking at C2, so we're looking at n is equal to 1. N is equal to 0 is the trivial representation, and so n is equal to 1 is a representation on C2, and it's also known as the spin 1/2 representation.
I have a question.
Yeah.
When we talk about, like, for example, like U1 or SU2, is it like this group of matrices the domain or the range of the representation function?
Domain. Well, so the pi. Well, for any. Okay. Let me get back to that. So these. Remember pi. So pi was a map from G, and if it's a if it's a linear, if it's a unitary representation, and these representations that we've seen, they all are unitary representations, then it goes to U of n. And I'm going to say more about. I'll say more about what this group U of n looks like. It's the group of unitary matrices. So pi is just a map from this space, which in general is it's a manifold. It's a nonlinear space, to this nonlinear space. So the pi these map as. This is what I was trying to get at by that picture I showed you a little while ago. That these maps they're maps from some nonlinear space to another nonlinear space, which is actually very hard to analyze. And but they have this very, very strong property that they're homomorphisms. That pi of G1 times pi of G2 is pi of G1 times G2. So they're very, very tightly constrained things, but they're as maps they're kind of horrible. They're maps between two manifolds. But so to analyze them, to make sense of them, we're going to take pi. What we're going to do is actually look at the derivative at 0, and that's going to be a map from the tangent space at 0 to this. So this is going to be a map from a real vector space with dimension of G, the dimension of the group. So in the case of U1, it was 1-dimensional. Today we'll see SU2, it's 3-dimensional. And then to the real vector space with the dimension of UN. Okay, and so these guys. So this is now. So the domain is just a real vector space.
Dimension here the real dimension of G.
What?
Is the dimension here the real dimension of G?
Yeah. So this is an incredibly confusing thing, which I'm going to get to later. But you have to keep track of. Anyway, that these, even though these things are acting on, you're thinking about complex representations on complex vector spaces. If you're trying to, you often have to think of them that these spaces are not the tangent spaces to these groups are not complex vector spaces. So they're real vector spaces. So this, it's some, and so becomes confusing, and I'll say a lot more about it later. But I think the main point is just that the whole reason for going from pi of these e to the I q1 theta down to just multiplication by q1 is that we want to linearize everything. And here, these maps are just nice. These are nice linear operators from from a vector space to another vector space. So these guys are just linear algebra. They're just, and if you have a basis, that it's just a whole story is about matrices. These guys are. This is not a story about linear algebra because these are nonlinear maps.
So in the case of U1, what would the group G be?
Just U1, so just the circle. So yeah, so G is equal to U1, and it's just the unit circle. Yeah.
So pi is from U1 to U1?
No, so U1 to then it depends upon how big the representation is. If the representation is on complex number on n vectors, then for each element in here, for each e to the I theta, you're going to get some n by n complex matrix, unitary matrix. So so here, yeah, you've got something fairly simple. It's just the unit circle. Here you've got this complicated thing, and that's why when I tried to draw a picture of it, I just made this kind of gray blob because it's hard to know what to. As we go through the course, we'll say a bit more about these guys, but they're very hard to understand. These spaces actually. So anyway, so the story for representations, the domain and range are these nonlinear spaces. We're talking about nonlinear maps. Here, when we take the derivative, then we've got nice linear maps, and everything is. We should be able to do everything in terms of linear algebra. Okay. Okay. Any other?
I have a question.
Yeah.
So just to clarify, the group UN is synonymous to like GL of some sort of vector space?
Well, so what I mean, I didn't actually. Let me say more about this. I think next time when I go over linear algebra. But I've been trying to avoid talking about general linear algebra. But the U of n means that they're unitary matrices. GLN means that they're just invertible, not necessarily unitary. That's all. Oh, but I'll say more about them next time. Okay. Else? Okay. So let me then get down to what I mainly wanted to do today, which is the and so what I was trying to say here is that okay, there's that if I tried to do the same thing that I did for U1 last time, what I'd have to do is I'd have to tell you what all the I'd have to figure out what all the irreducible representations of SU2 are, and that's hard. But the answer kind of looks like this, and at some point we'll go through it. It takes some work, but you can do it. So what we're going to do today, though, is just so from representation theory today it's going to be it's going to be it's the simplest. Anyway, maybe give it this fancy name of the spin 1/2 representation on C2. But the map here, when I said that pi map in general is complicated, well, here it's actually just the identity map. So pi from well, let me anyway. So pi is the identity map. But it takes a 2x2 complex matrix to the same one. Okay. So as a representation, I mean this whole subject that I'm talking about today, I think it can be confusing. I'm trying to tell you maybe you don't want to think about it in terms of representation theory today because it's kind of the world's stupidest representation. It's just if somebody gives you, a group element, a group given by matrices, and say, give me a bunch of a representation, which is a bunch of matrices that obey the group law. Well, you can say, well, I'll give you the stupid one. It just take the matrices, that take the original matrices themselves. And that's so it's called the defining representation, and it's kind of it's confusing that it's too easy. It kind of doesn't. It's very unclear why you would even want to talk about representation theory if you're just going to talk about these things. Okay, so today what I'm going to do is I want to talk about these things, and I want to kind of give some of the this is kind of the first system this is where you kind of get the first system that actually starts to really look like quantum mechanics, where you start to have observables that don't necessarily commute. So let me kind of start to go through this kind of carefully, and maybe so I'm going to start now, instead of from the abstract world and saying let's look at all representations. I'm going to start from the ground below and say let's look at find all, given that your state space is C2, find all self-adjoint linear operators. On C2. Yeah. So we could ask this question, if you really believe quantum mechanics is just a story about complex vector spaces and self-adjoint linear operators, well, let's take kind of the simplest, besides these one-dimensional cases, which we did last time, let's take the next simplest dimensional case. Let's take C2, and then ask what are all the possible quantum observables that could act on the state space. And so you want to find, what are all self-adjoint linear operators on C2, i.e. all matrices 2 by 2 is M such that so M dagger is M, but this, remember, but M dagger, this is the conjugate transpose. So maybe I should say that here. So M dagger, which is you take M, take the transpose, take the conjugate, and you want to set this equal to itself. So you want to find all 2 by 2 matrices that are of this form that do this. That if you take the transpose and you conjugate, you get this. Or if you like, you could also think of it, you could put the conjugation over here. It's just all matrices that when you transpose them, you conjugate. Okay, and so the answer is fairly simple. The answer is this. So the answer is that M is, well, one thing that does this, I guess I'll use the same notation, what did I call it? C1 and C0. So it's some constant times the identity matrix. I mean, the identity matrix is self-adjoint. But then there are 3 other things you can do. There are 3 other linearly independent matrices that are also self-adjoint. And there's, we're going to write them this way as a constant times something called sigma 1 plus a constant sigma 2 plus a constant and sigma 3. Okay. And so there's really kind of a 4-dimensional space of there are kind of 4 coefficients that tell you which which quantum observable you're talking about, what your what self-adjoint linear operator on C2 you're talking about, and these guys we're going to be seeing much of these matrices are 2 by 2 matrices called the Pauli matrices, and so sigma 1 is this guy. And you can see that he's obviously self-adjoint, because if you transpose him, you get the same thing, and he's real. And then there's sigma 2, and he's this guy. Oh, I'm going to always get the sign wrong. Minus 2. And then there's sigma 3, which is the diagonal one. Okay, so what we're going to do is we're going to mostly forget about the behavior, about this observable, about the identity observable. He's really boring. If you exponentiate him, you get your, anyway, you get back to your U1 story. And so we're going to forget about this. So we're going to be interested in what happens with these guys, and maybe the thing to do is to say where we're going. If you take C0 is equal to 0. Let's forget about that. And then let's look at these guys. Then e to the IM. So we're going to say this guy is kind of a generalization of our Q, of the quantum observable Q for U1. Now it's going to be for another group, but the e to the I m give elements of the group SU2, and this is this is 2 by 2 unitary matrices with determinant equal to 1. Okay. So we'll get to this. So one thing that you want to show, and one thing I'm trying to do computationally, is to try to develop some computational techniques so you can easily see what happens if you start exponentiating these guys. If you start exponentiating these guys, you want to understand what happens, and and I'm just telling you now the bottom line. The bottom line is what's going to happen if you exponentiate one of these. If you exponentiate one of these, is you're going to get all unitary matrices like that. And so now, so I'm starting kind of at the other end of the problem. I'm starting with the observables, with the self-adjoint linear operators, and I'm telling you, we can work our way back and see what group these came from. By so let's find the group that this exponentiates to, and the group is going to be this, and we'll get to that. Okay. Okay. Now, maybe before I get into that technology, now is probably a good time to say something about, so this is where kind of all of the a lot of the complexity of quantum mechanics actually appears here, and that this system is what's often called the called the qubit. So this is the qubit. It's in some sense, besides these U1 cases, which are really trivial, this is kind of the first kind of non-trivial case of a quantum system. And what you want to do is you want to say that the so H is equal to C2. Well, let's say it has a basis. Elements are this guy, and then this guy. So these are the basis elements of our state space. So you can give these a name, and I guess sometimes one standard way to call these things is call this one 0 and call this the state 1. Okay. You can do that, or maybe you want to do it the other way. I don't know. But anyway, so they're really kind of two. All states in this system are really just complex linear combinations of this guy and this guy. And notice that these guys, these are eigenvectors for sigma 3. Okay, so this particular observable sigma 3, which was this guy. So you have sigma 3 0 is equal to 0. So it's an eigenvector with eigenvalue 1, and sigma 3 1 equal to minus. I'm wondering if I've actually done. I'm not sure. I may have the convention completely backwards. But anyway, the point is that these when I made the decision to make one of the sigmas diagonal, and I decided to make it the three-dimensional one, then I kind of also picked out a basis in C2, which was the basis of eigenvectors of this diagonal thing, and that's this guy and this guy. So one thing you could do is you could write down so sigma 3 is an observable, and it has sigma 3 has eigenvalues plus minus 1. And so if you think of sigma 3 as sigma 3 is actually something you can imagine measuring. It's going to correspond to so we'll get into this in detail later, but you're going to get it. What you can often think of these C2 systems as corresponding to maybe an elementary particle that has this internal property called spin, and this observable corresponds to if you put the thing through a certain kind of magnetic field, it's either going to go one direction or the other, and depending which direction it goes, you're going to the eigenvalues would be you're going to measure whether this whether the correspond what you're going to measure this eigenvalue, and you're going to see whether it's plus or minus 1. So if you just had the observable sigma 3, this wouldn't be too interesting. You've just got you've got a C2, and you've got a everything proportional to this has eigenvalue plus 1. Everything proportional to this has eigenvalue minus 1, and that life is pretty simple. But here the problem then is this. So the complexity at sigma 1 comma sigma 3 is not equal to 0, and sigma 1 2 comma sigma 3 is not equal to 0. Okay, so here's the where all the problem comes in. The problem is that you can characterize your states by these eigenvalues of sigma 3, but the problem is that if you do that, these you can't maybe let me say what the bottom line is here. You can't simultaneously diagonalize by sigma 1, sigma 2, and sigma 3. Okay, so this is something that there is, we're kind of, by the way we wrote the matrices, we're working with the basis where this is diagonal, and these guys are not diagonal. But and so you can read off the eigenvalues here. If you change basis and diagonalize these guys, the other one of these guys, the other two are going to be non-diagonal. Okay, and so you can't. So what does anyway, let me just say this in words. So if you've got one of these states that has a specific eigenvalue of sigma 3, you diagonalize it. It has no well-defined number for the observables corresponding to sigma 1 and sigma 2. And this is the kind of weirdness of spin, that if you have this elementary spinning particle and you fixed its spin in this direction to be plus 1, then if you try and measure its spin in the other directions, it's not it just doesn't have, there is no well-defined answer to what that is. If you go and try and make a measurement, our measurement theory is going to tell you that half the time you're going to get, if you try and measure this guy, half the time you're going to get plus 1 and half the time you're going to get minus 1. So you then have this whole business with probabilities. Okay, so I think actually if you haven't seen any quantum mechanics before, this is also a recommendation for a good time is to find a quantum mechanics book that kind of starts by talking about the physics of the qubit of this. and I think one of them is Feynman's lecture notes. So Feynman wrote the series of books on lectures on physics, and the third one is about quantum mechanics. And I believe he starts up with something similar. He starts off with a similar system to this, and then you can and spends a lot of time kind of thinking about, you know, what could this possibly physically mean. So in terms of the physical significance, it's anyway. It definitely takes some getting used to, and I don't want to kind of spend. I don't want to spend time about this. So we're going to try to say something about how to kind of work with this mathematically in interpreting these guys as these guys are things that when you multiply them by I and exponentiate, these are just like Q. If you multiply them by I and exponentiate them, you're going to get a group element SU2, and that what you're looking at here is you're looking at the defining representation of SU2 on C2. So let me just kind of see what else I've got in these notes to the. Okay, so the trick about these calculations. Maybe let me do anyway. So I'm not going to go through all these calculations that are in the notes. You really have to kind of sit down and look at these things. Let me tell you the one of the main trick that makes these calculations really easy to do. So what we're going to do is how do we diagonalize linear combinations of this thing? Okay, so let's get this. So how do we? So there's a first property. An important property of the sigma matrices is this, that if you take so they have this property that what I want to tell you, that sigma, well, if you take sigma j and sigma k and add together the opposite one, but you're going to get twice the identity matrix. Okay, and so this is sometimes this, I'll write this as the anti-commutator. So I use a symbol for a commutator. I put a plus here because there's a plus here, and they say that this is equal to two times the identity matrix. Okay. So what you can do is you can take you can think of so define if you have let's define so if you have a linear combination of these. Let's define this. So let's think of this as v vector dotted with sigma vector. This is a vector of these three components are 2 by 2 matrices. So we're taking a dot product of a usual vector with a vector.
Sorry, I clarify 2 times identity. Actually, if you put j equals 2 and k equals 3, you'll see sigma 2, sigma 3 plus sigma 3, sigma 2 has no diagonal element. I mean, the diagonal element should be 0.
Is there a chronic delta jk in the right hand side?
Wait, sorry. Oh, so sorry. Yeah, thanks. Yeah, thank you. Yeah, thanks. Yeah, you're right. Of course. Yeah. Yeah. Sorry. Thank you. Yeah. Thanks.
Oh.
So sorry. Yeah. So the commutator is 0 unless it's the same thing, and then you get this. Yeah. Thanks. Sorry about that. Good. Yeah. So it's these are matrices that if you you multiply by them by themselves, you get the identity, and if you do this with that, you're going to get twice the identity. But I guess maybe a better thing to say is these have the sigma j sigma k is equal to minus sigma j sigma k for j not equal to k. That's another way of saying this. But thanks. Okay, so now if we define this, what's gonna what I want to exponentiate is I want to exponentiate, you know, these linear combinations of these things, and I can think of them in this language, that they're characterized by these vectors here. I mean, if you want okay, but now what we can do is we can add, now that we've got these, we've turned vectors into 2 by 2 matrices. I guess, I mean, maybe I could even write it out. It's well, anyway, you can look at that in the notes. But it's so this is just, given any vector, this is just the 2 by 2 matrix. So now what you can do, which you can't normally do with vectors, is you can multiply this thing by itself. Okay, and what you find that if you take v vector, so if you take this 2 by 2 matrix and multiply by itself, and you use this property, then what you'll find is that you get v1 squared, that you're going to get the identity matrix times the identity matrix. Okay, so if you start multiplying this thing by itself, if you just multiply it by itself, you're going to get, so you get the, you know, the absolute, the length squared of this vector v times, you know, this identity matrix 1 1 0 0. Okay, and so what finally happens is that so powers of this guy are then given by n are equal to well, if n is even, actually they're okay. So let's say that let's now look at so let's get rid of the problem of the length of the vector and take vectors that are length 1. So if we take linear combinations where the overall length of the corresponding vector is 1, then we do this. Then what's going to happen if we start multiplying this together? This is going to be 1, and if we take any even powers are going to give us just 1, and odd powers are going to give us just back this. So it's going to be 1 for n even and v vector dot sigma vector for n odd. So this is the so something very nice happens if you put these guys together in this way. And I guess what I want to claim so we're going to just use if v vector is, so if these v's are unit vector, then e to the I, if you take this linear combination and multiply by I, what you're going to get is you're going to get 1. Yeah, so you write out the the Taylor series for the exponential. It's 1 plus I v vector dot sigma vector plus now you're going to have an I, this guy I squared over 2 factorial and is v vector dot sigma vector squared plus etc. So you just write out the formula for the exponential as a power series, and then what you find is that these guys, all of the even things become an identity, and they're multiplied by this. Sorry, the calculation I wanted to do, I want to put the parameter back in here. So sorry about this, but I want a theta here. I want to put a parameter in here. So then there's going to be an I theta, and then an I theta squared. And so if you put together the even order terms, this one, etc., you're just going to get the identity matrix and times, and then a 1 minus theta squared over 2 plus other stuff, and you're going to get the formula for the cosine of theta. And then the even ones are going to give you an I times the formula for sine theta times v vector dot super vector. So I'm going to have to start finishing up, but the point, the nice thing about this computation is that what we're going to do is that we know we know very explicitly what these guys are. These guys are self-adjoint 2x2 matrices. But now using this formula, we also know that these are kind of nice linear operators. But when we exponentiate them, we get nonlinear operators. But we get but the nonlinear thing we get has this very simple behavior. And in some sense, what's happening is that, well, anyway, we'll say a lot more about it as we come to different applications of this. But then the idea, what I don't really have time to go through because we're getting to the end, but it is done in the notes, is we use this to show that that e to the I theta v vector dot sigma vector is an element of SU2. And so in other words, that it's so you want to show that it's unitary, and that its determinant is 1. Okay. So you can very explicitly show, based upon just the properties of the sigma matrices, the fact that they're self-adjoint 2x2 matrices, and that that you can get that these guys are unitary matrices and they're determinant 1. So in this group SU2. So that's the main thing. So this group SU2, we're gonna spend a lot of time talking about. We'll do a lot more with it. Maybe just the last thing to say before we get to the okay, let me just tell you one last thing about SU2, and then I'll leave the last part of these notes for let me pick up again with that next time. But so let's just say one other thing about SU2. And again, here I think what I won't do is I won't go through the calculation. I'll refer to the notes. But there's another way of thinking of another way. So you also have, and show that all SU2 matrices are of the form. So what you can do is you take alpha and beta, where alpha and beta are complex numbers. So if you write down let's say one row of the matrix, and then you can figure out you have to figure out, if the matrix is going to be unitary, then it turns out in order to make it be a unitary matrix, this has to be minus beta bar, and this has to be alpha bar. So the conjugate. Okay, and then in order for it to be unitary, it has to look like this, or I guess I'm not quite saying this right, but anyway, this will give you unitary matrices, and if you want the determinant is equal to 1, this corresponds to this times this minus this times this, which is alpha squared plus beta squared is equal to 1. And so these are sets of 2 complex numbers, so they're 4 real numbers. So what we've done is we've claimed that the sum of the squares of 4 real numbers has to be equal to 1. So this implies that SU2 is is the unit sphere, is the unit vectors in R4, C2. So I'm going to continually say that SU2 is a three-dimensional sphere. So what we saw before, we saw that U1 was if you like, a one-dimensional sphere, a circle. Well, what's this kind of next interesting group? It turns out the two-dimensional sphere is not a group, but it turns out the three-dimensional sphere is a group. You can put these, and it's exactly this group. Okay, so what the things that I still haven't got to, which I'll say a bit at the beginning of next time, which you should definitely look at before next time, is you can ask the same questions that I was asking about if you've got a map from S1, you've got a representation map from S1 to UN, and you want to take its derivative. What does its derivative look like? And you could ask the same thing. You could ask the same thing for here, for this, and there's a corresponding. So anyway, so all of the things the general things we asked about S1, you can start thinking about S3. Except it's much harder to think about it because you're in, a three sphere. You can't even really visualize because it's got it's unit vectors in 4 dimensions, but it's hard to see what 4 dimensions are. So let me kind of stop for this now. So next time what I'm planning on doing is finishing a little bit more of this to say a bit more about this, but please read the rest of what's in chapter 3. And then I think the other main thing for next time will be a kind of a review of linear algebra. So I've every so often as I've gone through, I've been talking about unitary things and about self-adjoint things and whatever, but I want to kind of go through the linear algebra and really kind of carefully say what we're going to use of linear algebra in arbitrary dimensions, and not because here everything is just kind of 2 by 2 matrices, so it's easy to deal with. But we want to be able to deal with arbitrary dimensions, and so we need some more linear algebra. Okay, so any questions about this stuff?
Yeah, I'm just wondering. So these matrices in SU2 of this form that you have up here with the alpha and beta, so those aren't Hermitian matrices?
No, they're not. And so I've given you 2 ways of thinking about SU2 matrices. There's this way, but notice though what I but I gave you or. I also said you can write them in the form e to the I theta times v vector dot sigma vector. Okay, so I gave you 2 very different ways of thinking about SU2 matrices. One is just this thing that they're kind of complex matrices, and once you know a row, you know what the other one is, and the determinant 1 condition says that the row has this condition, so these have to have unit length as 4-dimensional things. But then I also said you can think of them as what you get by exponentiating a parameter times unit vectors times the Pauli matrices. So I mean, these are 2 very different ways of thinking about it, but they're actually the same thing. So here you've also got this is 1 parameter, and these are unit vectors in 3 space. So there's 2 parameters here. So there's 3 parameters governing these guys. There's also 3 parameters governing these guys, which are this guy. So I'm kind of just starting to give you some different ways of thinking about SU2, which are quite different. And depending what you want to do, you're going to use different things. But this is really kind of crucial for like here. If somebody asks you, okay, you've got, if you have this SU2 matrix, how do I take its logarithm? How do I differentiate it? I mean, how do I think of it as the exponential of something? This answers the question. This doesn't tell you anything about that. This doesn't tell you. It gives you a different kind of information about SU2. So we're going to work a lot with SU2 and pick up different pieces of information about it. But this is just a start. Does that help?
Yeah,
okay.
Thanks.
Anything else? Okay, well, if not, one other last announcement. There's the course now has a TA, one of our graduate students, Davis Lazowski, and you may hear from him. He's going to set up some office hours if you want to talk to him, and he's the one who's going to be, and your first problem set is going to be due next Tuesday. And one thing is he's going to be grading the problem set. So if you want to complain about who the guy who graded your problems, that you could talk to him. But so besides being able to talk to me, I encourage you to stick around afterwards. After I close this down, we'll start. I'll be around for a while, and anybody who wants to talk can talk. Or if you don't have time now or some other time, let's set a time best for me on Tuesday and Thursdays when you can talk to me, and you'll also have someone else to talk to about the material. We'll understand who can talk about the material of this class, who's going to be Davis, our graduate student, and he's going to get going later this week. Okay, any questions? Okay, so I'll shut this down for now. Okay, bye now. Okay, bye.
I can do.
You can